So, building on the system of particles and rotational motion, where in the last lecture I told you about the center of mass and how to obtain the coordinates of the center of mass. If the coordinates of the position vectors Ri are known to us in the orthogonal coordinate system in the mutually perpendicular axes of x, y and z, okay, we could write this equation: m vector r is equal to sigma of mi ri vector ri, which I can split into m1 r1 plus m2 r2 plus etc. mn rn. Now, this is the kind of thing we have done before also for a particle system. Now, what we do from this equation, we can ddt this or differentiate with respect to time. So, what I get from here, capital M is a constant, dr dt, m1 is a constant, dr1 dt, m2 is a constant, dr2 dt, etc. mn drn over dt. Okay. Of course, we have taken that the mass is not a function of time. Okay. So mass is a constant in this relation, and I can readily write from the definitions that we have in the kinematics that dr dt is the velocity. I've written is capital V. dr1 dt, sorry, I missed this. Then I can write it m1 v1 plus m2 v2 plus and so on plus mn vn. It's very easy for you to do it. It's just a simple exercise in writing. And we get this relation where v1, v2, v3, vn etc. are the velocity of the respective particles, and v is the velocity of center of mass. Now, if I do ddt again, that is differentiate it with respect to time. So what I get here, like before, m dv dt, m1 d1 dv1 dt, m2 dv2 dt, etc., like this. And from the definition that we have for the accelerations, in the kinematics, acceleration is defined as the rate of change of velocity, the instantaneous acceleration associated with the system. And similarly, I can write this equation m1 a1 plus m2 a2 plus and so on, etc. Now this, if we look and apply the second law, Newton's second law, where F is equal to m dv dt or ma, then I can write this as ma, m1 a1, m2 a2 plus and so on, like this. Or I can just say that ma is equal to F by application of the second law, and there is an absurdity on my part, and that absurdity is that I have not put the vector sign over here, so I'm sorry for that. Please excuse me for that. So F is equal to ma is equal to f1 plus f2 for fn, or I can simply write that this ma is equal to f external. Now here, the f1 to fn, what I get here, f1, f2, fn, these things which I have written over here, each of them is a sum of all the forces which is acting on particle of mass m1. All the forces which are acting on the particle m2, internal as well as external. And we know that it is the external forces that matter. So therefore, this is actually, these are the vectors of external and internal forces, And internal forces, of course, they cancel out each other. So it is external forces, and I can write this relation MA is equal to F external. So this is, in a nutshell, the various relations that we obtain for the motion of the center of mass of a rigid body. If any body is comprised of many masses put together. Okay. So the motion of the center of mass is described by the MA is equal to F external. Okay. The center of mass of the system of particles moves as if the mass of the system were concentrated at the center of mass. So that we can treat the system as if it were a point object, and all the external forces these forces were applied at that point, that is the center of mass. What is that? We need not know the internal forces, the description of the internal forces associated with the system, and what we need is to know only the external forces. So with that, I'm just telling you an application. Suppose there is a body, and this body is projected at a certain angle, and you know that the track over here, the trace over here is a parabolic path that this body is going to attain, and at any instant of time during the flight there is an implosion. So let's call it explosion, and this body of mass m whatever is divided in many fragments, and the fragments move in different directions depending upon the instantaneous force or impulse that is applied on those particles. But what is an explosion? That is an internal process. So the center of mass of the body, which has been split, but the center of mass will keep on traveling along the same path. Maybe some of the mass it falls here, some of the mass it falls here, etc., etc. These things can be worked out in various conditions. Maybe the explosion takes place here, maybe explosion takes place here. So we can know the coordinates of this point, okay, with the x and y coordinates or r theta in the polar coordinate system, and we can work out, and it's not very difficult to work it out. So the next item, I come to the next item where I discuss the linear momentum of the system. Easy. So we extend what we have done just now to the case of linear momentum of the system of particles. As we know, we can define the linear momentum associated with the particle as the product of its mass, which is scalar, into the velocity, which is a vector. I have done it several times in the past few lectures, and that the external force acting the system, this is the definition, it is equal to dp dt. Look here, this definition of the Newton's second law applies always, even in the inertial systems as well as in non-inertial systems which are accelerating with respect to a frame of reference which is in the normal system. Now for the total system, I can write where the total mass of the body is concentrated, center of mass, and the body is center of mass moves with the velocity v. So the total momentum p I can write as the sum of the momenta p1, p2, pn, etc. Okay, and this has the total mass of the system, and this is the velocity of the center of mass of the system. Now it's very simple. What we go next, in keeping with what we have been doing in the dynamics, that rate of change of this momentum is equal to F external, or if I apply here, so m is the constant, so this becomes dv dt, and which is equal to m into capital A, where capital is the acceleration of the center of mass of the system. Now it's very simple. For the conservation law, okay, I can write that if the total external force in the system, F external, is equal to 0, then of course this is 0, that means dp dt is equal to 0, or simply that p is the constant, and so the momentum of the system is conserved. So it is about the linear momentum of the system of particles as well as the conservation of the linear momentum of the system of the particles. I am just taking an example. An example is that there is a radium nucleus or radium atom, because it's so heavy that we need not include the electrons, etc. What happens that there is, at this instant of time, while the system is in motion, there is a radioactivity, and it splits into two components. One is the radon, which has got a mass less than that of the radium atom, and of course there is a helium particle which has which is 4 as this, its atomic mass. So all it happens is split like this, but this will, the center of mass of the system while it occurs, this will continue to move in the direction in which it was heading, and the total momentum of the system will be conserved. That means the momentum in this direction, the momentum in this direction, they cancel out each other, okay, the mass and the velocity, and then the component along the y-axis and the component along the y-axis here, they will cancel out each other, okay, and they will add up to give the mass of the radium into its velocity that will be obtained on the x-axis. If this is taken along at the cosine of the velocity multiplied with the mass of the helium atom, etc., here the cosine of the velocity and the mass of the radon atom, etc., etc. This is the system in motion. But if instead the radium were at rest and the radioactivity takes place, so that the helium goes in the vertical direction, vertically upward direction, this will go in the vertically downward direction, or if this goes along the plus y-axis, this will go along the minus y-axis, plus z-axis, minus z-axis, plus x-axis, minus x-axis, etc. And at all moments of time thereafter, after it has taken place, this splitting has taken place, or the radioactivity has taken place, we can say that the total momentum of the system will remain equal to 0 like it was before. In this case, the total momentum of the system after the radioactivity has taken place will be the same which was there initially. There is another system in which is known as binary star. But what where I am placing you in the case of a binary star, where one star is going in this direction like this and the other is going like this. Okay. They have the same velocities. They are situated diagonally opposite. This is the diagonal and their situation is diagonally opposite. All the times, at all instances of time. And this is the center of mass of the system. And where am I? Where are you? If we want to look into this, then we have to go there, knock at the door of the center of mass and say, please let me stay here to see as to what is happening to this binary star. So that this frame of reference, instead of being away from this, the frame of reference is shifted to this point over here. Okay, and then while sitting over there, the center of mass will tell us where is S1 and where is S2, and this pair is diagonally opposite and they are moving in opposite directions. So not only the center of mass position is conserved, even the associated angular momentum, etc. calculations can be done. So that is about the linear momentum of the system of particles. Before that, what we have done? We have done the association of the motion of the center of mass system, and before that we have learned how to calculate the center of mass system. Next item, which I will take up very quickly, next time we meet, I have already done for you, and that is the cross product of two vectors. And the cross product of two vectors, I will again just introduce to you that if I have two vectors, one in this plane, in the plane of the board or the plane of the copy, etc., then this is one vector and the other vector of the same variety or a different variety, it doesn't matter at all, it makes a positive angle over here. So A cross B, how much is A cross B? A cross B is a new vector, and that vector is C, such that that vector is perpendicular to vector A as also perpendicular to vector B. So to this vector it will be perpendicular like this, and to this vector also it will be perpendicular like this. So it is a vector which is normal to the plane which contains A and B. I have already done that for you, so I request you to visit back to where I took the vectors and dot and cross product, etc., etc. So we meet soon and talk to you about this cross product and its application in the case of the system of particles and rotational motion. So long, thank you very much.